Good evening all. Am I audible?
Yes, ma'am, you are audible.
Yes, ma'am.
So today we will just take doubts from week 6 and 7. So the last time we had decided Tuesday's session, we'll clear doubts of week 6 and 7. So maybe we'll start off with week 7, reflect with us problem, because on discourse a lot of people had asked about it.
Yes, ma'am. Then we can do the grader
Is
tomorrow.
that fine?
Yes, ma'am. Yes, ma'am.
Yeah. Is my screen visible?
Yes.
Is my screen visible?
Yes, ma'am.
Okay, so the question is about affine spaces and affine mapping. Quickly, what is an affine space? What is an affine subspace?
Ma'am. Hello, ma'am.
Yes.
Sir, ma'am,
Yes.
please
Yeah,
also
I can hear you.
also explain the concept related to dot products. I have also doubt in dot.
Okay, fine.
Ma'am, can you once again explain the concept of affine,
what is an affine?
affine subspace and affine mapping for briefly for 5-10 minutes? Actually, I'm not able
an
to.
affine subspace is nothing but a translation of.
Yes, ma'am, I know that.
Is there a lag
What I do not understand is what is L and what is L prime or U prime. I don't know that, ma'am. Can you explain the concept for just 5 or 10 minutes?
Yeah, so it's U and U prime, they are just two notations that we use for subspaces. Just like how we use V and W for vector spaces, U and U prime are nothing but subspaces. Just a notation that we use for subspaces. And L and L prime are affine subspaces, that's all. This is the notation that we use. And an affine subspace is nothing but a translation of a subspace. Right? Yes?
Yes, ma'am. Clear till this point.
Yeah. And a mapping is said to be an affine mapping. So you define a mapping F from L to L prime, two affine subspaces. You have two affine subspaces. You define a mapping between them. So if L is an affine subspace, it's translation of the usual vector subspace. There is a vector subspace which is translated to get L. So which we denote as V plus U. V is any vector in L, and then U is the underlying subspace which is being translated. And for L prime, maybe we denote it as V prime plus U prime. L prime is the translation of U prime by the vector V prime.
Okay, both of L and L prime are the translated affine spaces. These are the affine spaces. That means they are the translated subspaces.
Yeah, so you have a subspace which passes through the origin. You translate that to get an affine space. So L. You translate U by the vector V. The distance that you have moved means you're adding the vector V to every point on the subspace U to get the subspace L. So L can be written as V plus U. V is the vector V. For L prime, we take it as V prime plus U prime. This is some other subspace which is being translated by the vector V prime to get another subspace L prime. So is it clear? U prime, L prime and all that?
Yes, ma'am. Now it is clear.
Okay. So if between two affine spaces, you define a map, a special map, which is called the affine map. So how this affine map is defined means, okay, when do you say it is an affine map? So you have two affine spaces, L and L prime. So underlying subspaces, U and U prime are there. Suppose T is a linear transformation from U to U prime. When you have two vector spaces, we can talk about a linear transformation between them. So suppose T is a linear transformation between U and U prime, then f of any point in L is going to look like V plus U, where U is in U, right? Because L is V plus U.
Ma'am, how you have written this step? Can you explain it once again, please?
Yeah. So L is V plus U. Is this clear? You translate U by the vector V to get L.
Yes, ma'am. It is clear.
So L is V plus U. What is the meaning of this? U is a subspace, V is a vector. How can you add a vector with a subspace?
We are adding this vector V to each and every point in U.
Yeah. So V plus U such that U is in U. This is the set, right?
Okay, you have
So
taken
any
small
element
U.
in L is going to look like this. Small u for elements, vectors, and capital U is for subspace. So now is it clear that f of an element in L is going to look like V plus U? Is this clear?
Yes, ma'am.
Madam, can we say that any linear transform, any transform which is defined by a function which is a polynomial of the order 2 and above, can we say that that's not an affine subspace? We can say that if any affine subspace,
Yeah.
Okay.
So you have a linear subspace, means the usual subspace that we have, and then you just translate it to get an affine subspace. So if you have a polynomial of degree 2 and all, that won't be linear, no? Means that won't even constitute, those set of points won't constitute a subspace. So translation of a subspace is an affine space. So you have to think along those lines. When you are given an affine subspace,
Okay.
the best thing is
y is equal to mx.
Best thing is to think, translate it to the origin.
Okay.
Yeah, y is equal to mx. Okay, that's a line. If it's two-dimensional, then it's going to be like what? Z is equal to lambda 1x plus lambda 2y. Something like this. So it's going to be lines passing through the origin or planes passing through the origin. All these are subspaces. So you just translate that to get affine spaces.
Ma'am, I had a certain doubt in the mock of 5 and 6, that mock paper.
Ma'am, can you explain
What is it now?
Oh, ma'am, actually, I didn't get like the 5 and 6, like conceptually, a 5th and 6th question. Like it's we have to fill in that space with the correct statement.
Okay. We'll do that. Before that, we'll finish this reflect with this problem, the affine space thing. Okay. Yeah. So this affine mapping is defined based on the underlying linear transformation. I guess there is a lag. Maybe I'll leave the meeting and join again. Is there lag? I feel there is.
Yes, ma'am. There is.
Yes, ma'am. Yes, ma'am. There is a lag.
Okay, I'll leave and join. Can you hear me?
Yes, ma'am.
Yeah. Okay. Now I guess it's fine. Maybe I should wait for them to make me forwards. 1 second. Just give me a second. I'll call. Okay. Can you hear me now?
Yes, ma'am.
Yes, madam, we can hear you.
Yeah. So, what were we discussing? Yeah, affine subspaces and all that. Yeah. So, yeah, what is an affine mapping? When we talk about an affine mapping between two affine spaces, what we look at is the underlying subspaces and a linear transformation between them. So, f of v plus u is going to be v prime plus t of u. T of u is well defined because t is a linear transformation on u, means from u to u prime. So, v prime plus t of u. T of u is an element in u prime. So this is an element in L. Is this clear? Did I share screen? Yeah.
Yes.
So is this clear?
Yes, ma'am.
Yes, madam, clear it is. Okay.
Okay. So now we will do the reflect with us problem, which is related to this. Okay. So we have two affine spaces, L1 and L2. L1 is U. Okay, the subspace itself is an affine space, right? You just translate by the zero vector, right? So L1 is
So, ma'am,
U.
we can say that every subspace is an affine space.
Yes, yes. Because the translation is by the zero vector. That's all.
Oh.
and L2 is 201 plus W. Okay. W is given, I guess. For some, okay, fine. For some subspaces, U and W of R3, okay. A basis for U is given. Okay, U is a subspace of R3 and a basis is given with 3 elements. So what is U? What is the dimension of U?
3 dimension.
Yeah. So what are the 3-dimensional subspaces of R3?
It is R3 itself.
Yeah. So for us, L1 is R3. And then W has a basis 10101. Okay. So what is the subspace W? 101011. What is this space? 101. What is this?
Dimension.
It's 2-dimensional, fine.
It's 2-dimensional, it's a plane.
Yeah. So you can write it as, when you have span of 2 vectors, you can write it as x times 0, 1, 0 or 1, 0, 1 plus y times 0, 1, 1. The span of this set is nothing but this. X comma y, alpha comma beta, anything you can take. I'm taking x comma y so that we can write it in terms of a plane equation. So this is nothing but x comma y comma x plus y such that x comma y belongs to R, right? I'm just multiplying this x inside. X and y are scalars for me. So I'm just multiplying. You're doing the usual scalar multiplication and then addition and getting this vector. So this is nothing but the set of all x comma y comma z, where z is equal to x plus y, right? The third component, you can write these vectors as x and y are varying. But based on x and y, the third component is varying, right? The third component is dependent on the first and second component. So I can write it as x comma y comma z such that z is equal to x plus y, right? X plus y minus z is equal to 0. This is my W, right?
Yes, ma'am.
Okay. So L2 is you're translating this subspace with the vector 2, 0, 1. Okay, L1 is given, L1 is R3 and L2 is this subspace. Okay, fine. Then suppose there is a linear transformation T from U to W. So when we are talking about affine maps, okay, this is actually talking about an affine map. So for that we need an underlying linear transformation that is given T from U to W such that 0, 1, 0 belongs to the kernel of T. And T of 201, T of 101 is given. Okay. You know the entire linear transformation if you know it on a basis, right? If you know T on a basis of U, then you know the entire linear transformation, right?
Ma'am, this means we can derive the expression of this transformation from T201 and T110, treating 201 and 110 as basis.
No, basis is given here. It's
No,
a 3-dimensional
transformational
space.
basis, the basis of the transformation. T201.
There is no basis for a transformation. See, basis for U is given. Some 201, 110, 010, 110, 010. And T is from U to W. So if I know T of 201, T of 110, and T of 010, then I know the entire T, right?
Yes, ma'am.
Yeah. Because any element...
This is what I wanted to say.
Any element U in U can be written as some alpha times 201 plus beta times 110 plus gamma times 010. So T of U is going to be alpha times T of 201 plus beta times T of 110 plus gamma times T of 010. Now if I know all these 3 values, then I know the entire linear transformation. But That's not given to us. Only for two values it's given.
Madam, can I
201 and
interrupt
110.
once? Can I interrupt once? You mentioned a little earlier that U is R3.
Yeah.
Do you mean to say U is actually spanning entire R3, or is it that it is of the third order or anything of that sort? Because
no, U is the subspace of R3 is given here, right?
U is a
For
subspace
some
of R3, so it is not R3, isn't it? It is a sub. It is.
A basis for U is also given. How many elements are there in the basis?
3.
And so the dimension of U is 3, right?
Correct.
How many three-dimensional subspaces of R3 are there? The only one, right? R3 itself.
Yeah. Got it. Thank you.
Yeah. Okay. So here we have T of 201 and T of 110. 011, 10. 011, 101. So only these two are given. I don't know the information about this, but instead I'm given some extra information. 010 belongs to kernel of T. Oh, that is also given. 010 is the basis vector. If it belongs to the kernel of T, what does
then
this
it is equal
mean?
to 0, 0, 0.
Yeah. 010 belongs to kernel of T. Okay. So now I know the linear transformation, right? Because I know the linear transformation on the basis elements. Okay. So yeah, maybe we'll go for the first three options. The first option is right, correct? We have already seen that, right? L1 belongs to L1 is R3, means the affine space that we got. L1 is equal to U. U is R3.
Wait.
Yeah. Okay. What is L2? We haven't found L2. W we found out. What is L2?
That L1 is equal to U is equal to R3. So
L1 is fine. What about L2?
L2 is what it maps to once you use the function.
No. L2 is the codomain. What it maps to is the range that we are interested in, but this is the codomain, and we know L2 is 201 plus W, and we know what W is.
Yeah.
So what is this set? This is the translation of this subspace by the vector 201.
Can you mute everyone? Please mute everyone.
If you're not talking to me, can you please? Okay. So what is L2?
L2 is translation by 201 of W. W is.
So what will you get?
X,
what
Y,
will
Z.
they be the affines?
X, Y, Z means like X plus 2, comma Y, comma Z plus 1, such that X plus Y minus Z is equal to 0.
Okay, fine. X plus 2, comma. Okay. Yeah. What you're saying is right. X plus 2 plus Y minus 0. Y plus 0. Okay. Minus Z. Okay. Maybe we'll write it like this, as you said. X plus 2, Y, Z plus 1, such that X plus Y minus Z is 0. Right?
Yeah.
Minus Z plus 1.
Yeah, I shouldn't be writing X plus Y minus Z. I'm abusing notation here. This X, this Y, and this Z, right?
Yes.
So it's going to be X plus 2 plus Y minus Z minus 1 is equal to 0, right?
Yes.
Minus of Z plus 1 basically.
Okay. We're substituting that in the
Yeah, you're just
equation.
moving by this point.
Okay.
So it's going to be x plus y minus z is equal to 1 or minus 1. Plus 2 minus 1. Yeah. Is that what we have here? Is equal to 1. Why did we get 1? Okay, just check.
I think
2, 0,
what
1.
you should do is you should consider x plus 2 as something else, and then in the place of x you have to substitute that other x minus 2, something like that we have to do, I guess.
Yeah, see, you need to do all this. As simple as this. This point should lie in the subspace, right? Means in the affine space.
Which point, madam? 201 should be lying in the
201.
affine.
Yeah.
Yes, yes, yeah,
It
correct.
should lie on the line. Yeah.
Correct.
So, and it has to satisfy this also. Means it has to be a shift of this. Only this
Yes.
number is going to change, right?
Correct.
0 is
Correct.
going to become something else. That
Yes.
you will get by substituting this point. That's all. Put 2, 0 and then 1. 2 plus 0 minus 1. 1. That's all. X plus y minus z is equal to 1. That's all.
That's easy actually.
Yeah. What we wrote down here, maybe we did something wrong. If we write it down v plus u such that u belongs to u, then we will get it correctly.
If we had substituted x as basically if we took x plus 2 as capital X or something and substitute small x as x minus 2 over there, then I think whatever you told it will match.
But I think we were getting a minus 1 there. So,
Yes,
no, I
madam.
mean you substituted x directly as x plus 2, but that's not the case, right?
oh, okay.
The x plus 2, the small letter x here and the small letter x there is the same thing. So we can't substitute x plus 2 in the place of x over there. We had to substitute, we had to consider this x plus 2 as something else and then write it in terms of small letter x and substitute over there. Then we would have got the other equation. I mean, it's same thing, whatever you told just now, I guess. Directly substituting and getting the coefficient.
Yeah, okay, fine.
Ma'am,
Yeah, so basically 0, 0, 0.
Ma'am, I am lost. I am lost. I'm not getting how you are getting L2. Can you
You
explain it
ignore
once?
all this. You just put this point on the subspace. 2, 0, 1. Put it here. 2, 0, 1. 2 plus 0 minus 1. Whatever number you get, that will be the number here for the affine space.
What is the logic behind this?
No, it's this. See,
Ma'am,
this is the base.
I have got till L2 is equal to 2, 0, 1 plus W. Till this point I am clear.
Yeah. So you have W is equal to something. It's two-dimensional, but I'm just drawing a line. Okay. So for us, we have a subspace like this. We want to find what is the equation of this line, right? So we know that these two lines are parallel. So the only thing that's going to change is this 0 is going to become some other number, right?
Okay.
Yes. So if I know any point on this line, I know what that number is, right? I now know it is of the form x plus y minus z is equal to d, right? For some d.
Okay.
Got it,
You taken it as TU. This is some number plus some. This is a transformation, right? Okay.
No, what? No d. We are talking about W now. Means L2 now. This is W. L2 is got by L dash. L dash, okay, L2. L2 is got by shifting W by the point 201, right?
Yes, ma'am.
So L2, the equation of L2, it's parallel to W. So it's going to be like this: x plus y minus z is equal to some d, right? Instead of 0, it's going to be some d.
Yes, ma'am.
So if I know
Got
any
it, ma'am.
point in L2, then I can find out the point value of d, right?
Yes, ma'am.
And I know 1.201. Right?
Yes, ma'am.
So with that, we'll get d.
But my major understanding got conflict, madam. Actually, we have an line in R3 passing the origin, and we shifted that particular plane to another by shifting 2, 0, 1, x coordinate to y to 0 and z to 1. Whereas when we have solved like that, it given -1. Whereas answer is
No. Here you ignore this. I was not using the right notation. See, I'm using the same x plus 2. That's not how it works. So you ignore this. If we have to do that, then we were looking at the set of all 2, 0, 1 plus x, y, z such that x plus y minus z is equal to 0. So we are looking at all the points x plus 2, 0, y, z plus 1 such that x plus y minus z is equal to 0. Okay. So now what? Yeah. We need to find all these points. And when will this be satisfied? Not when x plus 2 plus y minus z plus 1 is equal to 0, right? This z is different from, means I cannot, this is my new capital X, capital Y, capital Z, right?
Yes.
Yes?
Yes.
So now I have the set of all these points. I want to find out what is this. So
then actually it works now, madam. Like actually, if you substitute it back, it is capital X minus 2.
Right.
It works actually.
So,
whatever you said, it works.
Yeah.
Other
no,
gentleman was
there
also
I
saying
did a
something.
mistake by keeping the same x, y, z. That's why we got a -1 and all that. So now what is x? Capital X. Now I'm looking at the set of all capital X comma y comma z such that small x is x minus 2, small y is y, capital Y, and z is z minus 1 equal to 0. So now this is the set of all x comma y comma z such that x plus y minus z is equal to 1. Now is it clear?
Yeah, ma'am. Right.
This is L2. But the easiest way is this, the translation.
Values.
Yeah.
Could you scroll down?
Yes.
How to get a capital X minus 2 plus y, capital Y minus Z minus 1? How to get?
Did you understand this step to this step? I'm adding this point to all the points satisfying this. So when I add, I'm going to get x plus 2 comma y comma z plus 1. And now I want to find out what is this plane, right? X plus 2 comma y plus z plus 1 satisfying all these points. So I'm taking it as capital X, capital Y, capital Z. Means I want to find all the points on this plane. So for that, I'm taking it as capital X, capital Y, capital Z. Capital X is x plus 2. So what is small x from capital X? From here.
Okay, got it.
Ma'am, please solve one more example related to affine space.
Let's complete this and then go. Let's complete this and go.
Okay. So yeah, is it clear how we got L1, L2 and all that?
Yes, ma'am.
So L1 is R3 is right. L2 is this is right. L2 is not R3. Okay,
not.
Fine. Now an affine mapping is obtained by defining f of u is equal to 201 plus t of u. Which of the following are true? Okay. So now once we get the affine mapping, means to know the affine mapping, f of v plus u is equal to v prime plus t of u, right? Do you know t of u?
Yes. Ma'am, is this linear transformation?
Yeah. Yes. The linear transformation that was given.
T
So
of
it's
u is
already
u
given
prime,
on the
isn't it?
basis.
Yes, ma'am. We can calculate the expression from this one.
Yeah.
This on the screen.
That's
By
all, no?
calculating.
So this we know.
Yes.
This we know, and the point v prime is also given there. Some 201. 201 plus t of u. So with that, you just have to calculate t of u. That's all, and then add 201.
Can you show T of u where you have written it, madam? Sorry, I missed
I
that
haven't
part.
calculated. This is the given
Okay,
information.
okay.
T is given on the basis. So
Yeah.
using this, we can find out T of.
Okay, that matrix is what we are going to get, isn't it?
Not matrix, you will get a transformation.
Yeah. Transformation. Yeah.
So T of u is going to be alpha times T of 201. That is 011 plus beta times 110. 110. For this, it is 101 plus gamma times 0. So it's going to be beta comma what is this? 1 alpha plus beta.
Alpha plus beta.
Can you directly tell this is y comma x plus y?
Yes.
No, you cannot tell. It's not the standard ordered basis. You have to write x comma y comma z in terms of this ordered basis.
But equation, both are equations same.
Is it the same? No, it's different. Something and all is there here.
Easy. No, ma'am. L2 is similar to you.
L2 is fine. Okay. But how will I get the transformation? Means I want to know what is T of x comma y comma z. How will I know that? I know T of
201 is equal to 011.
You have to express x comma y comma z as alpha times 201 plus beta times whatever 110 plus gamma times 010, and then you have to find out what is this alpha, what is this beta, what is this gamma. Then I know T of x comma y comma z, right? Is it clear?
Okay. X equals to alpha.
No, x is not equal to alpha.
Yes.
2 alpha
2 alpha plus beta
is x.
Yes.
Beta
Beta.
plus gamma.
Yes.
Alpha, that's all. So z is alpha. X is equal to 2z plus beta. So beta is x minus 2z. Beta plus gamma is y. So x minus 2z plus gamma is y. So gamma is minus x plus y plus 2z. So T of x comma y comma z is equal to T of alpha z times 2 comma 0 comma 1 plus beta x minus 2z times 1 comma 1 comma 0 plus minus x plus y plus 2z times 0 1 0. And now these are numbers alpha, beta, gamma. I can take it out of the linear transformation and I know the linear transformation on the basis. Can you please mute if you're not talking to me?
Hello.
Plus this times 0 1. So you cannot write T of x comma y comma z is directly. You have to express x comma y comma z in terms of the basis elements and then write the transformation. This term is 0, so no problem.
0, 1, 1.
Zero, 1, 1, 1, 0. So this is x minus 2z, comma, z plus, okay, z plus this, so x minus z. So this is the linear transformation. So what is the affine map?
U plus T of U. B plus T of U.
Yeah. So it's going to be x minus 2z plus 2, z, x minus z plus 1. This one. This is the transformation T. This option is the transformation T. So to get F, you have to shift it by 201. So you'll get this. Is it clear? It's a step-by-step process.
Yes, ma'am.
Yeah, this is a nice question, right? You're applying all the concepts of whatever you've learned from starting from linear transformations till affine spaces.
Ma'am,
can you?
you
Sorry,
repeat?
ma'am. Can you just repeat like quickly?
Yeah. So we'll see here only. So what you first want to know is you want to know what an affine map is. An affine map is defined between two affine spaces. Affine spaces are translations of subspaces. So you have two affine spaces, L1 and L2. And then you define an affine map based on a linear transformation between the underlying spaces. Like this, f of v1 plus u is v2 plus t of u, where t of u is the linear transformation between the underlying spaces.
Hello,
And
ma'am.
then,
Is this just for this case, or it's always like this? Affine, defining the affine maps.
An affine map is defined like this.
Okay.
Hello, ma'am. We are already find T of U. So then why are you finding x, y, z in terms of linear transformations? Linear transformation of basis vector of U?
No, see, you know, you want to find out t of x comma y comma z, right?
Yes. Yes.
And I know that x comma y comma z can be written in terms of the basis elements,
Vector
right?
of
It's some alpha times this,
yes.
beta times something, plus gamma times something. These are my basis elements, right?
We can use T of U.
No, what is t of u? Means I just wrote
We are
a
already
general
finding.
u. No, I just wrote a general u. What is that u?
Okay.
This x comma y comma z has to be expressed like this, right?
Yes.
You have to find out what is alpha, beta, gamma. That's what we did here.
Okay. 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 Okay.
So we find out this alpha, beta, and gamma so that we know the linear transformation.
Okay, ma'am.
Yeah.
Hello. Yeah,
Yes.
yes. Ma'am, 010 is element of kernel T. Then T of 010 is 00, right?
Yeah, yeah.
But when it is not a standard basis, like when 201 is a kernel of T, then what the value of 201, T of 201?
Any element that belongs to the kernel of T, its image under T will be 0.
0, 0. Okay. Thank you.
T of 201 would have been 0 if it belonged to kernel of T.
Kernel T. Okay.
Yeah. So yeah, here we first found out what is L1 and L2, the affine spaces. And then we found out the linear transformation. Because we know the linear transformation on the basis, we just had to find out what is t of x comma y comma z. For that, we expressed x comma y comma z in terms of the basis elements, that 201, 110, 010 and all that. And then once we get the linear transformation, we know the affine mapping. You just have to shift it by the vector that is given 2, 0, 1. It's given here f is equal to 2, 0, 1 plus t of u. Is it clear?
Yes, ma'am, it is clear.
Yes.
Hello, ma'am. If I ask can we discuss some about inner subspace? I have some problem
Inner
there.
product spaces.
Hello, madam.
Inner product and norm also,
Hello.
ma'am.
Yeah, we'll do that. Yes.
Hello, madam. Could you repeat L2 part, madam? How do we get from figure?
No, from, okay, this one. See,
Yeah,
is
yeah.
it clear how we
Yeah.
got W?
Yeah, madam.
So I know that L2 is a translation of W, right?
Okay.
It's parallel to W. So the only term that is going to change is this constant term. Everything else is going to be the same, right? That's why they are parallel.
Okay.
So I want to find out what this constant term is going to be, what this D is going to be.
Okay.
For that, I know a point on L2. This is a point on L2. 201 is a point on L2. So you just substitute that in this equation, you will get D.
Okay, madam. Okay, thank
you.
Hello, ma'am.
Okay, so
One small question here.
Something I didn't understand. First of all, we are finding t of u. Then again, we are finding t of x, y, z. So
no, ignore this. No. See, what I did here by finding out t of u means I have to express this u as alpha times 201 plus beta times 110 plus. So you should know what this alpha, beta, gamma is, right? I just wrote in general t of u.
Okay, but both
After
the
you find
equations
out
are
alpha, beta,
different. That's why.
gamma. No. So ignore this. After finding out alpha, beta, gamma, you should plug that values here. That is what we do later on.
Yes, that I understood. But both equations are different. That's why my problem is created.
Ignore this.
Okay, ma'am.
Sorry, ma'am, can you repeat the last bit where you just struck it off? Why did we actually not go ahead? Because
this is correct. Here we have not found out alpha, beta, gamma explicitly.
Okay.
So what he was asking was this t is different from that t.
Okay.
It's not different because I haven't found out alpha, beta, gamma here.
Okay. So it is basically t of u is expressed as the basis vectors of.
Means I have just written now t of u here. I don't know what alpha, beta, gamma is, right? That's what we found out later.
Right. Got it.
Ma'am, one small question I want to ask. Can you show the equation of W, which we have got there? W.
Yes.
We have written in the last line x plus y minus z equal to 0 or x plus y equal to z. That means this is the equation of a line. And if we write it as
equation of a
x
plane.
plus
Two independent variables, no? So it's an equation of a plane.
No, in last line x plus y minus z equal to 0.
This is the equation of a plane. Oh, I was just drawing lines so that it's easy to identify.
Okay.
This is, if it was a line, it would have been something like this.
Can you mark a point on W and show where is it being translated? Suppose it is 0, 0.
This point here will go here. This point will go here. This point will go here. It's just shifted.
Right.
Yeah. Okay. And then, one more problem in affine space. Is it needed? Now is it clear? Someone had asked for another problem on affine space.
Ma'am, it is clear.
Yeah. Okay. And then what inner product spaces? What is the doubt in dot product? Yeah, someone was asking what dot product is.
Yes, ma'am, I was asking. I have not got the concept, but what is the logic of this inner subspace?
Inner product space.
Yes.
Right. An inner product space is nothing but, so you know what dot product is, right? What dot product is actually doing in R2, R3 and all that. You have two vectors And then dot product is actually going to give the angle between them, right? You know the formula and all that. Cos theta is
Yes,
equal to.
yes, ma'am. Yes, that I know.
Yeah, yeah. So in general, in abstract spaces, there is no concept of angle, right? We are talking about angles because we know in R2 and R3 we can talk about angles. But when we have abstract spaces, vector spaces, V, W and all that, we don't even know how the space is going to look like. So there we cannot talk about angles and all that. So this inner product is nothing but a generalization of the concept of dot product. So the dot product will be a special case of inner product. So you define something, you define a mapping. So there is a mapping from an inner product V, a vector space V to R. So this mapping satisfies certain properties. What are the properties for inner product? This V comma V has to be is equal to, yeah, it's equal to 0 if and only if V is equal to 0. This is 1. And then linearity, V plus W comma, okay, V1 plus V2 comma V3 is V1 comma V3 plus V2 comma V3, and then the scalar thing, alpha times V1 comma V2 is equal to alpha times inner product V1 V2, and then the symmetry property, V1 comma V2 is equal to V2 comma V1. So any function from V to R that satisfies these four conditions is called an inner product. And you can see that the dot product satisfies all this. So the dot product is a special case of this inner product.
So the opposite is not true, madam?
No, the inner product is more general, right? Dot product is just one of this. You've seen a lot of problems in the activity questions with different inner products, right? Which are not the dot product. Yeah. And then what do we do with inner? Norm. What is norm? Norm extends the concept of length. So when you have a vector in R2, so this is one point x comma y, you can talk about the length of this vector, right? It's the distance from the origin to this point, right? And in terms of the dot product, how do you find out the length of this vector? What is this? X1 squared plus y1 squared, right? The distance from the origin to this point is square root of x1 minus 0 whole squared plus y1 minus y minus 0 whole squared, right?
Yes, ma'am.
This can be written as x comma y dot product with x comma y, x squared plus y squared. So this is the concept of length in R2 or R3. In a general inner product space, we have the same concept being generalized. We have what is called as a norm. Norm is a function from a vector space to R satisfying those properties. What are the properties? The norm of any vector is always greater than or equal to 0, right? The distance of any point from the origin is always greater than or equal to 0, right? It cannot be negative, right?
Yes.
Yeah, so the norm is always greater than or equal to 0. And when is the length of a vector going to be equal to 0?
Vector is 0.
Yeah, if and only if the vector itself is 0. This is the first condition. And we have the triangle inequality, right? For distances. Yes, we have that mod of x plus y is less than or equal to mod x plus mod y, right? Okay.
Yes, ma'am.
I shouldn't be telling this. Yeah, but if you take any two vectors and then you add them, it's going to be the third side of the rectangle triangle, right? So the length of the third side is always less than or equal to the length of. That's this concept. Length of the sum of the lengths of the other two sides. And then what if I scale a vector? what is going to happen to the length?
Alpha time.
Mod
Yes.
alpha times, right?
Yes,
The
mod
length is
alpha.
going to get scaled by that magnitude of whatever is the scaling that's happening. So this is all what happens for the length. So using those conditions, you define length. There is no concept of length. What is length in abstract spaces? So you define what is this called as norm of a norm function. Basically, you find the norm of a vector, which generalizes the concept of length, the concept of length in R2, R3 and all that. Is it clear what norm, inner product and all is?
Yes, ma'am.
Okay. So yeah, what you want to solve any problems in this? I guess after this it's all pretty easy, right? Once you know these concepts, it's pretty easy to find out.
What time the inner product only can you please go back?
What is it? Inner product?
Yeah, only once. Can you explain?
You want me to tell inner product once again?
If possible.
Yeah.
Just explain it with an example, otherwise.
Okay. So an inner product is nothing but a function from a vector space to R satisfying these four conditions. So if you want to check whether a function is an inner product or not, you have to check whether each of the conditions are satisfied or not. Even if one is not satisfied, then it's not going to be an inner product. Okay. So maybe we'll take an example. Yeah. So is this an inner product? So in some sense, what does the symmetry condition say? So I want inner product V1, V2 to be inner product V2, V1. So what does that say when I have terms like this? Okay, firstly, am I allowed to have V1 squared, W1 squared, V2? Why? Which condition will be violated if I have squares? This one, right? The linearity. When you add two terms, it's not going to split. So this condition says that I'm not allowed to have squares or cubes or anything. I'm allowed to have only a single, means the highest power I can have is 1. What does this symmetry condition say? Let's take an example, which is from this example, what do you think the symmetry conditions say?
Should be 0.
No. Suppose I have a function UV is U1 V1 plus U1 V2. Will this be an inner product?
No, madam. You're not using
Why?
U2. U2 is not getting used, so.
Okay, let's use it here then. Okay, let's use U2. Is this an inner product?
No.
Why not?
Symmetry is still violated.
Yeah, the symmetry will be violated whenever you have cross terms and the other pair is missing. So you have U1, U2, V2, then you should have U2, V1. And you're not allowed to have 2 times U2, V1. Is it clear? Because I want f of u comma v. Huh?
Can you write the same thing near the conditions so that we can correlate?
I'll write the conditions here.
Yeah.
So okay, let's discuss condition by condition. U comma v, u plus v comma w is u comma w plus v comma w. So is it clear from this condition I am allowed to have only linear terms? So these
Yes.
are, I'm not telling mathematically, okay? So these are like cheat codes. So linear terms. What does the symmetry condition say? Am I allowed to have terms like this?
Oh, okay.
It will not reflect the other way. No?
Okay.
So u comma v, when you do u comma v, you will get this. When you do v comma u, you will get v1 u2 plus 2 times v2 u1. This is not equal. So whenever you have cross terms, means I mean mixed terms. In those terms, whatever is the coefficient, means if this is there, the coefficient of this has to be there for the other term as well. So this is not an inner product, whereas this will be an inner product, right? Means okay, at least symmetry condition. You don't want alpha u1 v2 plus beta u2 v1 with alpha and beta not being equal. Why is it not going to affect terms like this? Means whether u2 v2 is there or not, why is it not going to affect?
Because you can interchange them.
Yeah, means the first component of the first vector, first component of the second vector. So it's not going to affect even if I write it in means uv or vu, it's not going to make a difference here. The difference is made only when you have mixed terms like this. Means when the indices are different, right?
Yeah.
Subscripts are different. So the symmetry condition says that all these cross terms should have the same coefficient. So now
here what happened actually, u1 v2,
if I had 2 here, then the symmetry condition is violated, right?
yeah. If we have 1,
if we have 1, it's fine, no? See, you just write it down. You write down what happens to the symmetry condition when you have a 2 here and when you have a 1. You just write it down, you will know what is happening.
yeah, okay.
So it's like the cross terms where the subscripts are different, you should have the same coefficient. So here the symmetry condition is going to be satisfied, right? V1
Yes.
W2, V2 W1 has the same, and the others it doesn't matter. Here linearity is not going to be satisfied, right? I'm having
there is a sign same, no, madam?
There
Cross terms.
Where this one?
Yeah.
Yeah. The
Okay.
coefficient. Here the coefficient is -1. So coefficient means including the sign.
For v2 w2, what will?
So
That's not going to have any effect, no? Means
and
W2 V2, V2 W2, it's all the same.
Yeah.
I don't think there's an example where symmetry is violated. Yeah. Here. Oh, here also it's the same. Okay, fine. Yeah, what is it? Is there a doubt? Okay, fine. Then what happens when we have mod terms? Again, linearity will be a problem, no? Because mod of x plus y is not equal to mod x plus mod y, no? So we are not allowed to have mod and all. what happens when the same subscript terms have a negative coefficient? In this case, 3x1 y1 minus 5x2 y2. What condition will be violated when we have terms like this?
Positive.
Yeah, the positivity condition will be affected here. Not means what? What is positivity? This condition, not positivity. This equal to 0. Yeah,
Positive definitely call that.
that's called, yeah. So you can find non-zero vectors for which the inner product will be 0 when you have terms like this, right?
Please explain, madam, this.
Can you quickly give me a vector whose inner product with itself is 0 but b is not equal to 0? Are we missing out on any condition on inner product?
2 minus 1 minus 1.
We want inner product b comma v to be greater than or equal to 0, right? I didn't write that down. Right?
Yes, ma'am.
Yeah. Equal to 0 if and only if v is equal to 0. Okay. Can you give me a vector where this doesn't happen?
Two terms having negative term.
Why negative? Why you already have a minus sign here? Make use of that. Zero comma 1 will do the job, right? What is inner product? 0 comma 1 with 0 comma 1.
Ma'am.
3 times 0 times 0. Yes.
Ma'am, the last one which you were explaining, there also we do have -1 and +1. So it doesn't make any difference when we are saying only the U1 W, or it makes a difference. The previous example which you were showing, there was
This
-1. Ma'am, on the question itself, that there -1 was there, no? -1 +1 there.
This one.
Yes, ma'am. Here the coefficients is -1, -1, -1, but the first term is +1. So it makes no difference for while citing that it is similar or not.
No, see, you want cross terms can have any coefficient, but you want all the same subscript terms to have positive coefficient. Means this is not any written rule. It's like if it, I'm just giving you. I'm not telling that if it has positive coefficients, then it is an inner product. I'm telling if it has a negative coefficient, then which is the condition you're trying to attack? That's what I'm telling. Is it clear? What I'm
No,
telling?
ma'am, I could not.
I'm not telling
Ma'am, one
that.
small question. Can we attempt all these questions using this logic?
So what
I'm telling is, can we do this
this
always?
is not logic. This is just a way to eliminate. That's what I'm telling.
Yes,
or
ma'am.
a trick
It's
to
just
identify which are the points which will create a problem. Yeah, I'll tell you.
just an observation. Can we solve every question using this observation or technique?
Yeah. So what I'm telling is, I'm not telling that if you have only linear terms, then it is an inner product. I'm not telling that. But what I'm telling is, if it does not have linear terms, check whether this condition is satisfied or not. Okay? That's what I'm telling. So to show that it is not an inner product, it's enough if you just tell one of the points is not correct, right? So if it does not have linear terms,
Ma'am, that example, can you please explain? I could not understand.
Yeah, I'll do that.
Ma'am, 0 comma 1 is x1 comma x2 and y1 comma y2, na?
No, I want v comma v, inner product v comma v to be greater than or equal to 0.
This 0 comma 1, madam, it is x1 comma y1 or?
Oh, yeah. Okay, fine. Okay, then we have to change the vector. This is going to be x1 comma x2. Okay, inner product x1 comma x2 with x1 comma x2 is going to be 3 times x1 squared minus 5 times x2 squared, right?
Okay.
So this will still work, right? 3 times x1 squared minus 5 times x2 squared.
But do we need to solve it, madam? It is already minus 3x squared, isn't it? So it's going to be negative regardless.
Where? Which one?
Okay, sorry, my mistake. x1 minus x2. Okay.
So what I was telling is, if it does not have linear terms, try to check whether this condition is satisfied. If the cross terms don't have the same coefficient, try to check whether this condition is satisfied. If the same subscript terms has a negative sign, negative coefficient, try to check whether this condition is satisfied. That's what I am telling. Okay, I am not telling that if all this happens, it is an inner product, or if it is not an inner product or anything. I'm just telling you that these are the conditions that may fail because of these occurrences. Okay, so with this in mind, we'll go. Okay, this looks fine, right? The first problem. It is not having any problem with any of our conditions. Means whatever we found out, our observations, everything is being satisfied by this problem, right? There are no cross terms at all. So it's fine. And it's all linear terms. And then even the same subscript terms have positive coefficient. So everything looks fine here, right?
Ma'am, the previous one, are you explaining that one, or it is the new one?
We'll do all the problems in this activity using this logic.
Okay.
So this looks fine in all ways, right? At least the 3 points that we noted, right?
Yes.
So now you cannot tell because those 3 points are not a problem in this. This is an inner product. Now you should verify each condition for this, and you will ultimately see that it is an inner product. Means everything will be satisfied, and hence it will be an inner product. So you can verify. Okay, so this is not a problem. What about this one? All the terms are linear, so no problem. There are cross terms, but every pair is there. V1, W2, so V2, W1 is also there, and their coefficients are all the same, so no problem. And the coefficient of the same subscript terms are all positive, so it shouldn't be a problem. We don't know, but at least from our point of view, it shouldn't be a problem. So you have to verify whether all the conditions are satisfied and check whether it is an inner product or not. Fine.
Ma'am, here that coefficient plus like for V2, W2, that is similar with V1, W1, that for both positive coefficients are there. You mean to say that?
Yeah.
Because
Yeah, the
V1,
coefficient of V1, W1 is 1 positive. The coefficient of V2, W2 is positive 4. They
okay,
need not be the same, right? Means it's not necessary. In fact, one of the terms may be there, the other may not be there also, right?
In such cases also it will be similar. It will not be, because if the absence of one term will make that thing like it will not be similar, right? Means that symmetry condition will not meet.
No, why will it not be satisfied? Suppose my condition is this V comma W is going to be V1 W1. Why
Yes.
will symmetry not be satisfied? W comma V is W1 V1, no?
If one of the term is negative, then it will not satisfy.
No, even if it is negative, what is the problem? Oh, okay, fine. Yeah, if it is negative, yes, there will be a problem.
B1, either B1 W1 or B2 W2, any are negative, then it will be not satisfied.
No. See, symmetry will not be a problem. Positivity will be a problem because same subscripts, I want the coefficients to be positive. Yeah.
Yes.
Ma'am, then means like if W1 V1 is I do have, and also I do have also negative sign with it. Still I can say it is symmetry, right? Or do I?
Yes, symmetry will be satisfied. No
But
problem.
positivity will be a question. So with regard to that, I should disqualify this option. Okay.
What will happen if the other term is missing? Means I just have V1, W1. Which condition will be violated, you think here?
Ma'am, the second, could you please go to the options that checklist?
Ma'am, fourth condition.
Fourth is symmetry, it will be satisfied, no?
Fourth
Now my
one
inner
is similar to
product
that
is
only.
V1, W1. That's all. Only this term is there.
I think second.
First one,
why will the
ma'am, the
second
first
one
one,
have a problem?
is
This
it
part of
positive?
the first one, right?
Yeah.
Positivity will not be a problem because I'll get V1 squared. V comma V is going to be V1 squared. That will not be a problem. But this will be a problem, right? So I want all the same subscript terms to be present. I want all those terms to be present. I want their coefficients to be positive.
Third condition.
If there are mixed terms, third condition, the third condition will means it will be affected. This actually these two put together is linearity. Okay. So the third condition will mostly come into picture when we have mod and all that.
Didn't get anything.
Huh? You didn't understand anything, is it? Is that what you said?
Yes, ma'am.
Okay. So is it clear? Oh, the definition of inner product is clear, right? Any function satisfying these four conditions is an inner product, right? Do you know how to verify something is an inner product or not?
Ma'am, the first one you're saying only it should be greater than 0 means if it is only positive value has to be there, and of v is equal to 0. What exactly you mean to say, ma'am? The first.
No, this is if and only if. IEFF. This inner product is equal to 0. Inner product v comma v is equal to 0 if and only if v is equal to 0. Okay, so who said I did not understand anything?
Actually, ma'am, I'm not see lecture. That's why I didn't understand anything.
Okay. So this cheat code, what I'm talking now is not then the lecture. In the lecture, it is the actual content. So now we are trying to find tricks to find out whether something is an inner product or not by looking at it.
Ma'am, could you solve
Maybe
problem
you can
with
do one thing.
numericals, madam? Numerical
Yeah.
vector like some 2, 3, 4 in R3, R4, something.
Yeah, we'll do. So, sir, maybe you can watch the video lectures, then come back to this portion of today's session, then everything will make sense.
Ma'am, in third condition, ma'am,
I didn't watch length and angle or inner norms. Those lectures I didn't see. All other lecture I saw.
Yeah, so this comes in that only, sir. So it comes in those last two videos. So you can watch that and then come to this portion of today's session. Then things will make sense to you.
Okay, ma'am.
Ma'am, in third condition,
yes,
alpha v1 comma v2 equal to alpha v1 comma v2. In this condition, always alpha value of alpha is equal to 1. Otherwise, how can I satisfy?
No. Why? Whatever is the alpha that I'm multiplying here should come out of the inner product. That's all it says. If it is -2, then -2 has to come out. If it is 5, 5 has to come out. If it is 1, obviously it is satisfied. But otherwise also it should satisfy.
In the case 3, you have written alpha v1 comma v2. That's all.
Means v1, v2 are all vectors. Let me write it as w. I was running out of alphabets, so
Ma'am,
Now is it
can
clear?
you please explain with example? That means numeric value.
Yeah. W comma V.
Whether I am reading right or wrong, I don't know. Alpha V comma alpha W it should be, or how?
No, no.
Just
Alpha is multiplied for the first.
vector.
Yeah.
How dot product and inner product, how similar the both are?
Dot product is also an inner product. So it is an inner product if it satisfies all these conditions, and the dot product satisfies all these conditions. So it is an inner product. Fine.
Ma'am, one small question. Like the inner product is from V to R. Could it be from, say, V to R2 or V to R3?
No. The output is always a number.
Okay, because
That's
it is
why you're
always a
able to
scalar.
compare.
Okay.
Yeah. Okay. So let's take this example. The inner product of V comma W is defined as V1 W1 plus 5 times V2 W2. So V is V1 V2, W is W1 W2. So our inner product is defined from R2 to R. So how will I check whether this is an inner product or not? Okay, it's still not an inner product. We need to check whether it is an inner product or not. So what will we do to check whether it is an inner product or not? What is the first thing we'll do?
Check the first condition that it is always greater than or equal to 0.
Yeah, and it is equal to 0 if
when
and only
V
if
equal to 0.
Yeah. So what is inner product V comma V?
It is
inner product V1 V2 comma V1 V2. The inner product says first component of the first vector into first component of second vector plus 5 times second component of the first vector into second component of the second vector. So what will we get?
V1 square plus 5 V2 square.
Yeah. First component of first vector into first component of the second vector. V1 into V1. V1 squared plus 5 times second component of the first vector into second component of the second vector. That's how it is defined. In the place of W1, W2, you again have V1, V2. So you'll get this.
How you wrote V1 comma V2 comma V1 comma V2?
Because I am doing inner product V comma V, not V comma W. Same vector I am taking inner product. Means V.
Had it been V comma W, then we would have taken V1, V2 and W1, W2, right?
No, we would have taken this. V1, W1 plus 5 times
So
V2.
while taking the vectors in last line that you have written, suppose let us say the vectors are V and W.
That's what is this, right?
Yes, it will be V1, W1 plus 5 W2, V2.
V2W. That's how the inner product is defined, right? For two vectors V and W.
Okay, now sorry to ask this at this time. Now can you tell what inner product is? Because now you told V1 comma V1, you are writing it as V1 comma V2. Okay.
No, that's a notation that I am using.
V equals V1 comma V. Belongs to R.
Inner product is, I'm talking about this function. I'm checking whether this function satisfies those conditions.
Okay.
If it satisfies, I will tell it is an inner product. So the first condition that I'm checking is whether inner product of V with itself is greater than or equal to 0 or not. So for that, I am calculating inner product of V with V. The definition that is given to me is when I have two vectors V and W, their inner product is defined like this.
Okay, okay. So first you are defining V equals V1 comma V2 and W as W1 comma W. That is what you are
that's the
calling
notation that we are following. Yeah.
Oh, okay.
And the inner product is defined like this. This is the definition of the inner product.
Okay, V comma W is equal to, okay, that's what you are expanding here. Okay, V1 square plus 5V2 square.
Ma'am, how can we conclude that this is positive V1 square plus 5V2 square? Because
this
there
is
is
a
no
square
negative
number.
This is square number.
Okay.
This is a square number. This is a square number. When I add, it's always going to be greater than or equal to 0.
If there is a V1 square minus 5V2 square, then?
Then it won't be satisfied. No. That is why I said in the cheat code that you're not allowed to have minus terms for same subscript terms. Minus coefficient. Right?
No. Can you go back to that checklist?
This one.
Rules.
So this is not a rule.
Yeah.
This is a trick. So suppose you had a minus. If I had V1 W1 minus 5 V2 W2, then this would have been a problem, right?
V2 W2.
If I had V1 W1 minus 5 V2 W2, then here I would have had a problem, right?
Yeah, it may be less than 0.
I can always give a vector for which it will be less than 0, no? I can always make this quantity big enough so that this becomes negative, right? I can always choose numbers such that, yes?
So it won't satisfy and hence it's not an inner product, right?
Yeah. So that is why I am telling that we want the coefficient of same subscript terms to be positive.
If it is a different subscript and if it is a minus, it's not an issue.
Yeah, it's not an issue, no? We have seen, no? This is an inner product.
Can I ask one doubt in that?
Yeah.
Please, can you suppose, ma'am, V2 is, suppose, don't erase. Suppose V2 is, let us say, 0, 1, 0.
Okay. No, what?
0, 1, 0. It is from
No,
R2. Okay, 0, 1.
Okay.
And W2
so
is equal
B1.
to?
This is B2. That's the notation we are following. V1, V2 for V, W1, W2 for W.
Okay, ma'am, let W be, say, 0, minus 1. If I don't write minus 5 in the equation written above, I write plus 5 and multiply. Then also I get negative.
No, I am not interested in V, W. No, I am interested only in V, V to be greater than or equal to 0. I am not at all telling this has to be positive. V, W can be anything. But when I take inner product of the vector with itself, it has to be greater than or equal to 0.
Okay, with its.
Yeah.
Ma'am, then here V1 value is 0 and we will multiply with the again V1, so that will come 0 only, right? That will be equal to 0. So is that the thing you are
This one?
Yeah. So here I will say B1 square plus B2 square. So now it will become 0 plus 1 square will be only 1. So that is value is 1 and that is greater than 0. That is what you're doing. Okay. And even though if it is 0 minus 1, still it will become greater than 0 only.
Yeah. So there was someone who asked, no, what cross terms having negative sign is not a problem. So what happens when we have cross terms? When we have cross terms, what happens to the positivity condition?
Ma'am, if V1 W2, V2 W1 is less than V1 W1, then it is maybe positive.
No. It becomes like this, right? When I take V, V. right?
Yes.
No,
Yeah, so
I am
these are terms.
confused.
These are terms which can be absorbed into a perfect square, right?
Actually, when we cannot say anything
Yes,
about
yes.
these terms, they could be
A
negative,
minus
they could
one
be
is also.
positive because they are cross terms. But we have to check the
Yeah.
condition for every vector with itself, v comma v. That is why the condition.
So it is this. When I take b comma v, I'm
And
going to get this. And these terms can always be absorbed into a perfect square. That is why when we have negative coefficient, even for cross terms, it's okay. But for these terms, we are not allowed to have.
Okay,
If
now I got
condition
it.
1 satisfies, then I will proceed for condition 2 and condition 3.
Yeah, even if one of them is not satisfied, you stop there. Because once something is not satisfied, it's not an inner product. Everything has to be satisfied for it to be
It
an
is a
inner
step-by-step process. I
Yeah.
have to first check condition 1, then condition 2, then 3, in this way.
Yeah, you can check it in any order, but this is the usual order that we follow. All the conditions have to be satisfied. In fact, symmetry might have been the second condition according to the lecture, right? Or it's these all the four conditions have to be satisfied. That's it.
One more example can you take?
Ma'am, please,
I
please
still have
continue
not
with,
finished this.
please continue this example with condition 2, 3, and 4, please.
So this is the first condition. So what happens when v comma v is equal to 0? Inner product v comma v is equal to 0. I need to check whether it is possible only when v is equal to 0, right?
Yes, understood. Understood.
Will it be satisfied?
Yes, ma'am, because we have to apply this operation on the vector with itself.
Yes, right.
So I'll get this. When will this be equal to 0?
When both v1 and v2 equal to 0. Otherwise, it could be positive, it could be negative.
No, it will always be positive.
Yeah, here in this case, it would be positive. Suppose this is not +5, this is -5. It would be negative.
No, see, if it was -5, then you can tell v1 squared is equal to 5v2 squared. In this case, it is not compulsorily equal to 0.
Yes.
But in this case, you can tell it's equal to, means each component is equal to 0 only when you have a plus. Sum of non-negative terms equal to 0 implies each term is equal to 0. Right? You agree?
Yes, yes, ma'am.
Yes, ma'am. Yeah. So that is what we are following here. This is a non-negative term, this is a non-negative term. Their sum is equal to 0. It means that each of the term has to be equal to 0. Because even if one of the terms was positive, then it wouldn't have been equal to 0. So now first condition is over. Second condition. V comma W, V plus U plus V comma W should be equal to U comma W plus V comma W. Is the practice assignment solution uploaded?
Yes, ma'am.
Then I think you can check in that, because in that everything is given in detail. Instead of us wasting time here, you can check there. It is there, no? So in that, I think everything is in detail. Means at least the first problem was completely. Yeah. This is norm, checking whether it is a norm. Everything is there. You can check here. See, everything is there here. This problem. You can check this problem. Whether it is an inner product or not, how you check and all that. So you'll do it from here. You just have to do substitute each vector and all that and check. Or maybe we'll do this. You do the other two conditions. Okay?
Yes, ma'am.
Ma'am, that V1 minus V2, what you have written, that was not a inner product, ma'am.
Which one?
V1 minus V2 is square.
Ah, no, no. When you have minus, you can make it 0, no? Even when the vector is non-zero.
Yes, yes. So that's not an inner
Here,
product.
right?
No, the above page, what you have across. Yeah, this one.
No,
The
no, this
lowest
is an
one.
inner product. This is that second example. This is an inner product because V1 inner product V1 with V1 is V1 squared minus V1 V2 minus V2 V1 plus V2 squared. This is nothing but V1 minus V2 whole squared, no? Oh, you're telling this condition V1 is equal yeah. Inner product V comma V is equal to 0 if and only if V is equal to 0 will not be satisfied.
Yes. So that's why it is not inner product, right?
Yeah. So this will not be an inner product. If I didn't, means if I have this term, then it is not an inner product. Is it clear to everyone that in this case it is not an inner product because this?
No.
Check this condition for this inner product. This is the inner product. Check this condition.
Ma'am, the first condition we got checked and we confirmed that because first condition is satisfied, and when we are checking the second one, so did you continue that from that only, or is that just are you flipping to the first condition again?
No, no, this is another inner product. Here we have continued the first example.
The second statement are you checking now, or the first statement?
We'll check the second one. First one is over, no?
Yes, ma'am. The second and third one we are you explaining that?
Yeah, I'll do the second one. V1 W1 plus 5 times V2 W. Okay. So what is inner product U plus V comma W? What is U plus V first of all?
V plus V, ma'am.
U plus V. U1 means we are all in U. All these vectors are in R2. U is
Yes.
in R2, V is in R2, W is in R2. So U1 plus V1 comma U2 plus V2. This vector inner product with W1, W2, right?
Ma'am, how can you expand this? I cannot relate.
So no, this is in R2. This is in R2.
In the condition 1, you put everything as a V. But in second condition, we retain the U, W and V, W.
Yeah, because that is the condition for
When
inner
you
product.
check the first condition, you put, when we expand it, V comma V, everything will be in terms of V, V1, V2, V1, V2.
Yeah.
But in second condition,
it will be different. Yeah. So how is the inner product defined? You take the first component of the first vector, multiply with first component of the second vector. What is the first component of the first vector here?
U plus V.
U1 plus V1, first component alone.
U1 plus V1, okay.
Into the first component of the second vector, that is W1, plus 5 times second component of the first vector into second component of the second vector.
Okay.
Right? Now you want to bring it to this. Can you bring it to this? What is inner product U comma W?
No, confused.
What is U? What is the vector U? Where is the vector U first of all?
U1 plus V1.
No, no, not plus V. No, 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 no. Where is U?
No, I'm
This is the
confused.
question, right? Means the question says inner product is a function from R2 to R, right?
Okay.
Yes, this is the means my inner product that we started with is from R2 to R, right?
Okay.
And I said this defined by inner product V comma W is equal to V1 W1 plus 5 times V2 W2, where V is V1 V2, W is W1 W2. This was the question, right?
Yes.
Okay. So where is V?
It is an R2,
U
ma'am.
plus V is the V.
V is in
V is in R
R2.
square. R2.
This function is defined for these two dots, which are elements of R2.
Okay.
So if I want to write inner product U plus V comma W, where should this U plus V be?
In R2 only, ma'am.
All the vectors on which we are talking about this particular inner product should belong to R2. And only if they are in R2, I can talk about this particular inner product. Is it clear?
Yes, ma'am.
Little bit, ma'am.
Okay. So now this is given. If I have V is equal to V1 comma V2, W is equal to W1 comma W2, defined by inner product V comma W is equal to this. So what is V1? It is the first component of V. W1 is the first component of W.
Yes, it is clear.
So now
Yes,
if
it is
suppose I have a function defined on R3 to R given by V comma W is equal to something. So how many components will we have?
3.
Yeah. But will the inner product have 3 components?
U1 plus.
No, ma'am, no, because dot comma it is defined in dot comma dot.
The inner product is always a function which is defined for 2 variables. Means you cannot have f of x comma y comma z for inner product. Means you cannot have dot comma dot comma dot. Inner product means it is for 2 only. But where do these elements belong? That is what is this. So here it will be like V1 comma V2 comma V3 comma W1 comma W2 comma W.
Okay.
So this represents where the vectors come from. But the inner product is always defined only for 2. Means in the sense that you can talk about inner product of 2 vectors only.
Okay, ma'am.
So now let's get back here. U plus V comma W. Where is U plus V?
R2.
R2.
U is in R2, V is in R2, U plus V is in R2, right?
Yes.
And W is also in R2, and then you can talk about the inner product of U plus V, which is a vector in R2, with another vector in R2, which is W. for this to be an inner product, I want this to be equal to inner product U with W plus inner product V with W. Again, U is in R2, W is in R2. So I can talk about inner product of these two. V is in R2, W is in R2. I can talk about this inner product, right? Whenever you have an inner product, you have to use this definition.
Okay.
Yeah. So what is U plus V?
U1, V1, or U2, V2, comma U2, V2.
U1 plus U1, U2 plus V1, V2. That is U1
Yes.
plus V1, comma U2 plus V2.
Vector elements of U is U1, U2, and vector elements in V is V1, V2. That I am going to say. And in
So what
W,
is
it is
U plus
W1,
V?
W2. Is
So
U1,
what is U
V1,
plus
comma U2, U1, V1, comma U2, plus V2. U1 plus V1,
plus V1,
comma U2 plus V2.
Yeah. So this is correct, right? What I've written here.
Yes. Yes.
So it has two components. It is still in R2. I'm taking inner product with W, which is in R2. W1, comma W2.
Yes.
So how is the inner product defined?
V1 W1 plus 5 V2 W2. And V1 means first component of V1. That means U1 plus V1. Okay, I understood the expression.
So now is this clear?
Yes, yes.
What is inner product U comma W?
U W. U means U1, U2. W means W1, W2. That means U1, W1 plus 5 U2, W2.
Perfect. What is V comma W?
V1, W1 plus 5 V2, W2.
Yeah. So somehow I have to start from here and I have to end up here, right?
Yes.
I already have the terms, right? U1, W1 plus V1, W1 plus 5 times U2, W2 plus 5 times V2, W2. I just have to combine them, no?
Okay. Basically, it is U1, W and plus V1, W. Okay.
Yeah. So is it clear to everyone?
Yes, that means condition 2 satisfies for this problem.
Yeah. Condition 2 is satisfied.
Then I got all that, but I have not got how the condition 2 is satisfied. The last line you have written.
So what is inner product U comma W? U1 W1 plus 5 times U2 W2, right?
I'm not getting this last line.
Okay. So is this clear? Forget this.
Yes.
You have expanded this, you've
yes,
got this.
Yes, yes.
Now you expand this. If you get the same thing, then these two are equal, right?
Right.
So when you expand the right side, what will you get? Let me write it down. What will you get now?
It is U1 plus W1. So sorry.
U1 W1.
U1 V1.
No. U comma W. So it's U1 U2 comma W1 W2 plus inner product V1 V2 comma W1 W2. What is this?
The inner product is defined as first component of first element of vector and first element of second vector plus 5 into first element of second element of first vector into second element of second vector. In this way, if we expand, we can get the expression, I thought.
Okay.
So what is this? What is this?
Ma'am, U1 W1 plus 5 U2 W2.
Clear, sir?
Yes.
What about this term? What is this?
V1 W1 plus 5
5 V2 W2.
Yeah. Is this equal to what we got earlier? U1 W1 plus 5 U2 W2 plus V1 W1 plus 5 V2 W2.
Yes.
So is it clear how to check?
Yes, ma'am.
Yes.
It's
So
good.
can you do the other two, symmetry and scalar product? Means alpha.
No, you please help.
No, you are doing. You tell me how to do it. So you want to show alpha times v comma w is equal to alpha times inner product v comma w. So what will you check here? What is alpha v?
Alpha into V1 comma V2. Yes, alpha into
Right.
yes.
So what is alpha v1, alpha v2, comma w1, w2?
Then alpha V1 W1 plus 5 into alpha V2 W2, I thought.
Alpha v1 w1 plus 5 into alpha v2 w, right?
Yes.
What should you prove this is equal to?
The right hand side.
Alpha is coming out and it is equivalent to right hand side. If you take alpha common.
I am really confused about this third condition, but it's very easy.
Yeah. That's it, right?
Yes.
Yes.
Symmetry, that's the simplest. No cross terms at all. What is this?
V1 plus 5, V1, V2, V1 plus, yes.
What is W comma V?
W1
V1 plus
W1 V1 plus 5
W2
V2.
All are same.
They're same, right? Fine. Is it clear?
Ma'am, good. It's good.
Over, no? All four conditions are satisfied.
Yes.
Yes. Thank you, ma'am.
So will you check like this for the others too?
Yes, ma'am.
So the easiest method is checking directly. How should we do, ma'am?
This is how you should check. You should check all the four conditions. So what I was telling, the cheat codes, that is giving a trick as to which of the conditions may not be satisfied. So if you have terms with square, means instead of this condition, V1, W1, suppose if it was V1 or V1 squared W1, then when I do this squared, I'll get a squared here. It's not going to be equal to what I actually want, right? You're going to have extra terms.
What I understood is if there is a minus for the same subscript, then it doesn't satisfy.
What doesn't satisfy?
If it is B1 into W1 If it is a minus for the other V2 minus 5 W2 V2, then it won't satisfy.
Yeah. So if you have same subscript terms with negative coefficient, it's going to be a problem for inner product V comma V to be greater than or equal to 6. Right?
Yes.
And square terms, if there are any square or cubic terms or anything like that, any higher order terms, then linearity V1 plus V2. So what is that? U plus V comma W is not going to be equal to U comma W plus V comma W, right? Why is it so? Suppose U1 plus V1 squared W1. If I have this, what happens?
It won't satisfy linearity.
So when I expand, I'm going to get U1 squared W1 plus V1 squared W1 plus 2U1 V1 W1. This I want for these two. This is unwanted, right? Right? I want to get this. These two will be available here, but this is an unwanted term, right?
Yes.
So that is why when you have square or cubic terms, this condition will get disturbed. Is it clear?
Yeah.
What
Yes,
I'm trying
yes.
to tell? I'm not telling that if these conditions are not set, means if these problematic terms are not there, it is an inner product. I'm not telling that. But I'm telling if you have these terms, then which are the points where there may be a problem. So instead of checking all the 4 conditions, suppose the order in which you have written, according to that order, suppose this linearity condition is the last, the other 3 may be satisfied. After checking all that with so much pain, you go to the last condition and check that it is not true. Instead, now when you know that there is a problematic, means when you have a square term, you go check this first, right? Okay, I think I'm talking too much.
No, ma'am.
That's a trick.
So you understood the trick, right? That it is actually a trick and then what is mod? When you have mod, again you mod x plus y. When you have mod of u1 plus u2, this is not equal to mod u1 plus mod u2. So I will not be able to connect these two, right? This is not always true.
Right side is better, right?
Yeah, so we'll have something like this. So that's not what I want. I want equality. So and then that cross terms, that is also clear, no? When you have cross terms with different coefficients, symmetry will be a problem. That's the easiest trick to observe, actually.
Ma'am, like the moment when we see there is a square term, we will check the coefficient one, which is a class term, and if the coefficient is, let us say, multiplication of 2 or 5 or something, then immediately we can say it is not meeting the conditions, right? Or would you ask?
Can you repeat?
Ma'am, like when such terms appears, like for example, u square w1 and b square w1, b1 square w1 plus 2u1 b1 w1. So in such cases, square term I should not see. I should see only the class term, which is a multiplication of any numeric number. Let us say 2 twice.
No. When you have something like this itself, it is not an inner product. No.
So from there itself, I should stop checking other terms as well, right? Or no such conditions I should check.
To show that something is not an inner product, you want to show that at least one of these conditions is not satisfied, right?
Yes. And
Suppose,
equality term will not satisfy then.
Any one of the 4 conditions is not satisfied, you want to show. Suppose this is the condition. This is the inner product. So now because there is a square, you go check this condition first. This condition. See, to show that something is equal to something, means if these two are equal, if I want to show, I have to expand everything and then show. But to show these two are not equal, it is enough if I choose one particular u, one particular v and one particular w, right? If it is equal, you want to show it is equal for all u, v, w in R2.
Yes,
right?
yes, ma'am.
But to show it is not equal, it is enough if I just show it for one set of u, v and w, right?
Yes.
So pick any one. Pick u is equal to say 1, 0, 0. Or maybe we'll pick 2 because 1 squared is 1, no? So let's pick 2. And v is equal to say 1, 0. W is equal to say 1, 0. What happens to this condition for these 3 vectors? What is inner product u plus v comma w?
That will be 2 plus 3 comma 0. Yes.
And then
it becomes 4 comma 0, ma'am.
No. What is how is the inner product defined?
3 square 1
9
plus
into 1.
0 0.
Yeah.
0
What is inner product u comma w?
Four.
2 square into
2 square plus into 1 plus, okay. What is v comma w?
1.
Yeah. So when you add these two, you get 5, which is not equal to 9.
Yes.
Okay. So now suppose, so this is over. Now suppose we have v1 w1 minus v2 w2. Now which condition should I target?
Greater than 0, 1. First
Still
condition.
positive.
Yeah.
So I want to try and show that this condition is not satisfied. So what vectors should I choose? In fact, I want to show inner product v comma v is not greater than or equal to 0. For that, what should I show? What v can I choose?
Ma'am, v2 w2 should be greater than v1 w1.
Exactly. So what should I choose for v as v?
1 comma 2.
Okay, fine.
For
That's
w.
all, right? Why should I choose w? The condition I want to check is v comma v, no?
Okay. Sorry.
So this is going to be 1 squared minus 2 squared.
4 square. 2 square.
So this is less than 0. Right? Next, suppose I have v1 w1 minus v1 w2 plus 2 v2 w1 plus v2 w. Now what condition should I target?
Symmetric.
Yep. Because the cross terms are having different coefficient. So now pick any vectors. Pick a vector v and a vector w. Just random. Say 1, 1. And w is say.
By different terms, are you saying, different coefficients? Are you saying it can be positive, negative, or a 2 under 1? 2
2 and a minus 1. Okay, even if it was plus, different coefficient. Okay, let's put plus. Yeah. So let's pick some random V and W. What is the inner product V comma W?
Uh, 1 into 2 plus
1 into 2 plus
1 in
2, 1. Yes.
Plus 2 times.
It is
1 into
1 into 2.
2 into 1 into 2.
Then
Plus 1 into 1.
2 in
No.
V2 W. So
yeah,
1
V2
into
V2 W2 is 1 1, yeah.
1,
So
2,
2
3, 4,
1
5, 6,
3.
7, 8.
Yes.
What is W comma V? 2 into 1 plus first term here.
1
Second
into
term.
1 into 1.
2 into 1, right? 1 W. 1 W. Yeah. Plus 2 times V2 W1. You just write it in order so that it will be V2 W.
1 into 1.
Yeah. Oh, is it matching? 2, 4, 6, 7. Okay, thankfully it's not matching. I'm not telling it won't always match. See, that's what I was trying to tell. But these are conditions where you can target and check.
By observation, you can guess means which condition should not satisfy.
Yeah.
Means,
So is it clear?
Yes, ma'am.
Madam, if you have some time, can we go over similar matrices and equivalence?
Yeah, sure. What is the doubt?
Essentially, when we say similar matrices is more about B is equal to P into A times P inverse.
Yeah.
How many possible P's are there, madam? Is it anything like unique, or we have infinite number, or what is that? Because the text, whatever I read, it only states we cannot determine P.
Yeah. So there is a way by which you can find P, but that necessarily doesn't say P is unique. There is a way by which you can find P. And even in this, Q, A, P. In this also I had told a procedure, right? How to get P and Q when the basis is given.
Yes, base is given, yes.
Yeah. With using the basis, you can find one such P, one such Q. And here also you can find one such P. But that doesn't guarantee that that is the only P. But why are you bothered about the infinitely many P's? You just want one, right?
Yeah, yep.
Yeah. So if the basis is given, then you can find this P, Q, or this P. But if the basis is not given, there is no algorithm to find P, Q, or this P. In which case you have to put P is equal to say A, B, C, D, and then check whether this condition is satisfied, all that.
And we can find Q as well, right?
Yeah, like it is a very tedious process because you have to put, see, in this case at least you'll if it's a 2 cross 2 matrix, you'll have only two means A, B, C, D, and then this P inverse will again have A, B, C, D. But here it will have an A, B, C, D. Here it's going to have E, F, G, H. So it's even more difficult for equivalence of matrices. That is why. But one nice thing about equivalence of matrices is they are equivalent if and only if they have the same rank.
Yeah.
So you just need to check the rank. But that is a big disadvantage for similar matrices, that you don't have a characterization. You cannot tell that if this happens, they are similar. Okay. You can only tell if it is similar, then this happens. That's not what we want. We want a condition which will tell that, okay, if this condition is satisfied, then they are similar. But we don't have such a condition.
Ma'am, I have a confusion regarding this matter. Ma'am, when we calculate standard order pair, we take always the basis of elements in R3 as 1, 0, 0, 0, 1, 0, and 0, 0, 1.
Yeah.
And sometimes we take 1, 0, 1, 0, 1, 1, and 1, 1, 0.
No.
Why?
Standard ordered basis is this E1, E2, En.
No, there
Means
is a
that
gamma and beta. If
this standard means it is only this. This what you were telling 1, 0, 0, 0, 1, 0, 0, 0, 1.
0, 0, 1.
This is the only standard ordered basis. Every other term is just an ordered basis. Means every other basis. If the term standard is mentioned, it is only this.
No, in the tutorial, I found that T alpha and T beta, they calculate two standard order pair, and the basis is different. I don't know.
Yeah. So see, that's not the standard ordered basis. Standard ordered basis means this.
1, 0, 1, 0, 1, 1 like this.
That is a different basis. That's all. That's a different ordered basis. Or you know what a basis is. Ordered basis means you want to maintain the same order. Means if you have a set 1, 2, 3, which is the first element in the set? There's no first element, right? Because this set is also equal to this set, right? This is also equal to this set. So this is a set. But when you talk about an ordered set, then this is not equal to this. Because in an ordered set, the order matters.
So how can I set the basis? Is there any rule?
If the basis is given to you, use it. Otherwise, choose any basis you want in any order you want. Because if the basis is not given, it means that you're allowed to choose. There are infinitely many bases.
By combination of 0 and 1 only?
No, your choice. 1, 1, 1, 1, 1, 2, 1, 1, 4. No, 1, 2, 4, something. Anything.
Okay.
Your choice.
And for if it is in R2, then suppose I take 1, 0 and 0, 1, and on the contrary, again I take 0, 0 and 1, 1. It is okay.
0, 0,
Suppose
1
I
and
take 0, 0 and 1, 1.
No, 0, 0 is not a basis, no? Means if 0 is there, it is not a basis, no?
Then what are the options for R2? Suppose I take 1, 0 and 0, 1.
You can, this is another basis.
Okay.
You can choose any two vectors which are not linearly independent, no? Then you get a basis, right?
Okay, actually I am confused with order 2, R2.
Madam, a small question based on what you just said a little earlier. Similar matrices are not defined not defined in the sense they are not identified with the rank being the same. No. But equivalence, when you say rank is the same, and we say similar equivalence matrices, similar matrices can be equivalence matrices, correct?
Similar implies equivalent, yes.
Similar implies equivalent. Then would it not be something like if matrices are similar, the rank is the same?
If matrices are similar, similar implies same rank.
Similar implies same rank.
Not true.
But the converse is not true. Yeah.
Okay, same rank does not imply similar, but similar is. Yeah.
Okay. We want something which will imply that it is similar, but we don't have something like that.
But ma'am, determinant is similar.
Yeah, they implies same determinant, but converse is not true. If they are same determinant, then they need not be similar. The simplest is this. Any matrix which is similar to the identity matrix has to be the identity matrix.
Okay, I have a question from activity thing, activity 7.1. The first question, the first option. Somehow I just picked it and I got it right. Yeah, but this one I was not able to. When I actually was looking at it, I didn't really understand what it means. The 3 by 3 matrix A is similar to identity matrix of order 3.
So what is given? I have a 3 by 3 matrix,
yeah,
and I have the identity matrix. So if these two are similar, what does it mean?
That is a big.
No, definition.
Yeah. P inverse into, okay.
Right?
Okay.
What is I times P?
It's P itself.
What is P inverse P?
I.
So A has to be the identity matrix, right?
Sorry. Yeah, in such a long sentence, I got lost, I guess.
Yeah. So if you are given a long sentence, just write down whatever is given. Try to proceed step by step. Yeah.
And P inverse of I will still be I, madam?
Yeah. Why not? Any matrix you multiply with the identity matrix, you get the matrix itself,
Same
right?
matrix. Okay. Yeah.
Ma'am, can we write similarity B is equal to P A P inverse?
Why not? This is equivalent to telling A is equal to P inverse BP, right?
Okay.
You can fix whichever one you want as the definition.
Okay, professor said in one lecture, they solved the question like that B is equal to P inverse AP.
Okay.
So here I can confuse and we solve this question P inverse AP. So that is not similar to B.
No. Okay. You want PAP inverse, right?
Yeah.
Put Q is equal to P inverse. That's all. B is equal to P inverse AP is what the professor says. You want P to be in the front. So that's going to be QA Q inverse. That's it, right? It's just a matter of notation, right? If you want PAP inverse, your P will be equal to the professor's P inverse, right?
Pardon, Mama, I could not understand.
Okay. You want this to be the definition, right?
Yes, ma'am. P B is equal to P inverse. Ma'am.
The professor says this, right?
Yes.
But you prefer this, correct?
Yes. Can we
Now the
write it
professor.
at similar time? P inverse AP or P inverse?
No. Now the prof would have solved and got a P, right? You take that P inverse to be some Q, some other matrix.
Okay.
The inverse can be treated as some other matrix, right?
Okay. We mean write it Q P inverse as a Q.
P inverse as Q. So P inverse is going to be Q A. P is going to be Q inverse. This is what you wanted, right? This is what you are comfortable with.
Okay, ma'am. We can write as.
Yeah. But since sir has stuck to this thing, all of us are doing the same thing. P inverse A.
Yeah, ma'am. I confused in that one and took more time to spend on that one.
No, it's all equivalent.
Madam, on the same 7.1, can you go to question 8, please? one of the options is E is a singleton set, and in fact that is true in this case. How do I determine that? Okay, maybe I'll just go back to the question itself. When we say
this is exactly the same as 7.1 question 1 option 1.
Oh, okay.
Instead of identity
matrix.
3, that's all.
It's a scalar matrix.
Scalar
Okay.
matrix.
Okay. All right. So when we say E is a set of 2 by 2 matrices which are similar to scalar matrix A, then basically here going by the rank and the determinant, can I say 9001 is also similar to this, or can I not say it?
No. In fact, you will find out, you have already given the answer. E is singleton set. Every matrix is similar to itself. Right? So you already know which is the matrix which is similar to. Means you already know the elements of E, right? E is a singleton set, and you know that E has one of the elements as the matrix itself. So that is the only element, right?
Okay.
See, you know, if you have a homogeneous system of equations, if it has a unique solution, what is the solution?
0.
Because you know that already 0 is a solution, right?
Yeah.
Yeah. So now you're telling E is a singleton set.
No, that's what probably I should come to the singleton set a little later. But when I actually am reading the first sentence, E is a set of 2 by 2 matrices which are similar to scalar matrix A. Then
you
the
just have
conditions
to write it down. E
okay.
is the set of all matrices A such that, or B, whatever, what is given. A is given. Okay, so let's take it is the set of all matrices B such that B is similar to A.
Yeah.
So what does this mean? It is the set of all matrices B such that B is equal to P inverse AP.
AP, yeah.
Now you know what A is. B set of such that B is equal to P inverse 3003. So if it is a scalar matrix, I can write it as P inverse 3 times identity P, right?
P. Yeah.
There's nothing special with this 3.
Okay.
So it is a set of all B such that B is equal to 3 times P inverse IP, right?
Which is finally boiled down to I.
What is this?
I.
And what is 3 times I?
3 times I is again the same matrix.
A.
Yeah.
Right?
Yeah.
It is the set of all matrices B such that B is equal to A. So it is the singleton set A, right?
Yeah.
3A, na? 3A.
No. A is 3 times identity.
Right. Understood, ma'am.
Yeah.
Okay.
You just write down what is given, do it step by step. You will get.
So when can we say there are more okay, as long as the condition P inverse AP is satisfied and there are many kinds of P, then there are infinite possibilities. Okay.
Yeah.
So in question,
And
if there is any other matrix like any ABCD matrix element or ABCD, then there also we will have the same answer, singleton set. Suppose
No. Why? Take I am not sure, but let's attempt. I want BP is equal to okay. I don't think it's gonna work. In 2 cross 2 it may be difficult to construct. I mean, actually there's something, some concept which you don't know that I'm keeping in mind and
So
trying to
we just
construct the matrix. But it's not the case. A matrix may be similar to multiple matrices.
Okay, so I was thinking means it should be exactly similar, so there should be only one means all elements should match. It is not like that.
No. There is another example, no, where here A and C are similar. They are not exactly the same matrices, right?
Yes, yes.
Yeah.
But in that case, actually, P, there can be infinite possibilities, no, madam? Whatever you're just trying to show.
There may be infinitely many P's satisfying that B is equal to P inverse AP.
So even if I were to actually come up with the matrix multiplication on left hand side or right hand side, like AP is equal to PB, and try to determine, will I be able to even get it? No, I don't think so.
Yeah, you just need to plug in some. We had done some 3 cross 3 example. I remember I had written A, B, C, D, E, F, G, H, I, and all that in the previous session, that Friday session.
Okay.
So in that, we were just plugging in values so that we get an invertible matrix P. That's all. I think for this example, yeah, for this example, yeah, I was doing something, I remember. So maybe you'll get a bunch of equations. So it is your choice what you put. Means I had chosen values in a certain manner, but you could have chosen in any other manner to get the matrix.
Okay.
Ma'am, the syllabus of quiz 2 is from 5 to 8 or 1 to 8?
1 to 8.
That means determinant is included.
Yeah, without knowing determinants, you cannot check whether two matrices are having the same determinant and then similar and all. That's fine. So you need to know all the concepts. That's it.
Yes. But most of the question is from vector.
Vector space, right?
Okay.
No, see, the thing is, here we were doing some problem where we had to solve a system of equations, right? Yeah, that A, B, C, D, X, Y, Z is equal to alpha times, yeah, here. We are actually solving a system of linear equations here, right? So you cannot tell that I don't want to study week 2, so I will study from 5 to 8 and write the exam. This is actually using week 2, right?
Actually, too many concepts in vector chapter. That's why we are getting, I am getting confused sometimes.
Yes, ma'am, understood. But mostly the questions will be concentrated on linear transformations and these affine spaces, no?
Yeah, so these will be the topics of interest, but concepts will be, since all the concepts are involved, everything is equally important. You cannot
I
forget
agree. I agree on that part, but the questions will be concentrated between 5 to 8.
Yeah, you can tell that, but you shouldn't tell that you asked to find a basis. Basis is week 4. That's not okay. Like that's why we say
That I
that
agree.
everything.
That I agree. Yeah.
Yeah.
And one more thing, time permits. Can you can you explain us a problem in norm also, norm of the vector, if it's okay with you?
Yeah, I'm fine. I'm free.
Ma'am, please upload today's note. I have to conclude the graded assignment 7. That's why.
Okay, fine.
Ma'am, one doubt on the same concept. In previous session, you wrote a formula like Q lambda 1 in terms of lambda 2. into A beta 1 in terms of lambda 2, something like that, and P beta 2 in terms of beta 1. I didn't understand that formula and why it is used.
No. That's not. Oh, okay, that one. Similar matrices. How to get
similar
P and
matrices.
Q.
Yeah. Because you were
For
discussing the
equivalent
same
matrices,
topic,
right?
that's why I asked.
Okay. So we'll do the norm problem. Before that, maybe I'll just tell this.
Sure.
Yeah. No, I'll tell the equivalence first. So, ma'am, is that okay with you? The one who asked for a norm problem?
Yes.
Yeah. Okay. So, equivalent matrices. Suppose you are having two vector spaces. Say beta 1 comma beta 2 are bases for the domain, and gamma 1 gamma 2 basis for the codomain. So you when I want, okay, so T from V to W, if I take beta 1 for the domain and gamma 1 for the codomain, I can write the matrix of the linear transformation, right? Given a linear transformation, I can write the matrix of the linear transformation, right?
Yeah.
Yes.
Yeah.
And then for the same linear transformation, if I use different bases, I'll get a different matrix. I may get a different matrix, right?
Yes.
So
But both are similar.
No, both are equivalent.
Equivalent.
Yeah. So now we know A is equivalent to B. So if A is equivalent to B, then B is equal to Q, A, P for some invertible matrices Q and P. This much we know. So I told you there is no algorithm to find out this P and Q. The basis is not given. But now that the basis is given, I can directly find out what is P and Q. So for P, for P, I need to write it down first. So B is beta 2, gamma 2. Q is the codomain. Q corresponds to codomain. A corresponds to domain. So if this is gamma 1, this has to be gamma 1. This will be gamma 2. P is, if this is beta 1, this has to be beta 1. So this will be beta 2. So for P, to get P, you write beta 2 in terms of beta 1. To get Q, you write gamma 1 in terms of gamma. So after you write this down, you will get a matrix, right? When you write beta 2 in terms of beta 1. Say suppose you have 1, 0, 0, 1, 1, 0. This is beta 1. Beta 2 is standard order basis. What do you mean by writing beta 2 in terms of beta 1 is beta 2 elements of beta 2 in terms of elements of beta 1. This 1 times this plus 0 times. This is a basis, this is a basis. So I can write elements of this in terms of this and elements of this in terms of this, right?
Yeah.
Because both are bases. 0, 1, 0 can be written as minus 1 times 1, 0, 1, 1, 0, 0 plus 1 times 1, 1, 0, right?
Yeah.
So the matrix P would be 1, 0, minus 1.
Okay.
Similarly, for Q, this is domain. P is domain, Q is codomain. And you should also note that the order is reversed. Like you remember this. So I didn't remember whether beta 2 in terms of beta 1 or beta 1 in terms of beta 2. When I wrote this down, I knew what is in terms of what. And how do we remember this?
We can cancel out.
Yeah, it's not actually cancelling out, but to remember.
Yeah. It's like a trick.
Yeah,
remember.
Madam, one question here.
And order will also be fixed for this formula. B is equals to QAP. Order of matrix.
Yeah, that's, see, you can write B is equal to PAQ also. But if you write PAQ, your P will be equal to my Q. That's all. Yeah. Just like that P inverse thing that we were discussing. PAP inverse, P inverse A. Yes, sir.
Madam, can you scroll up a little bit, please?
Thanks.
Up a little bit. Yeah.
Okay.
No, I mean to say where exactly you are. Yeah, this one. So when I'm going from A to B, how am I actually determining that it is beta 2 to gamma 2?
No, I know B is this, beta 2 to gamma 2. Means the notation that I use is codomain, domain below, codomain on top. This is the notation that we use. T, basis for domain, basis for codomain. Yeah.
And here actually it could be even beta 1 to gamma 2, right? It could be anything. It is just that we are picking these bases. That's all.
Yeah, it could be beta 1, gamma 2. Means you can choose the basis that way also.
Okay. All right.
Okay.
Ma'am, if we will not have 2 lambda, then we can use 1 lambda only.
Gamma.
Sorry, gamma.
It is based on. Gamma 1 will be equal to gamma 2 there. That's all.
Yeah. So we can use same for both.
Yeah. So on Saturday, I forgot to tell this. On Saturday and Sunday, we will leave mock quiz 2 open. So take your time and solve mock quiz 2. And we will cancel Saturday's session so that you can solve the quiz 2 thing. Week 8 contents are not much, so we can finish it off in 2 sessions.
So ma'am, week 8 content will be there or not in the mock?
Yeah, it will be there. Most of it will be covered in Friday's session. Yeah.
Okay.
Madam, I have a separate question, but don't get me wrong when I'm asking this. I only trying to understand what it is. When you say linearity or bilinearity, going back to inner product, linearity or bilinearity, what is the physical interpretation to it? Is there something like, okay, I can use this in this particular application, that's the reason why I'm doing it, or what is the...
I am not sure about applications. I don't know much about it.
Okay.
So I won't be in a position to answer this.
Okay. Can I interpret linearity and bilinearity as a single line even if I go left or right, or how is that? Or is it just commutative property kind of a thing?
Maybe I will look up for it and post it on Discourse if I find something interesting, because I have no idea. Yeah.
Okay.
Let's do a norm problem.
Yes.
Ma'am, inhomogeneous, non-homogeneous, what is the mean of?
What is the?
Professor says in Affine lecture.
What does he say?
Homogeneous, inhomogeneous, non-homogeneous, non-inhomogeneous.
In affine space, is it?
The solution set to a system of linear equations.
Oh, yeah. This Ax is equal to 0. The solutions of Ax is equal to 0 forms the subspace. Ax is equal to B forms an affine space. This I had discussed in my session, the Friday session.
Okay, ma'am. Actually, ma'am, I'm suffering from eye allergy from 10 days. I attend this session. All the previous session I could not attend due to I could not see the proper screen on that.
Okay, it is all on YouTube, right? You just have to go to the calendar, your Google Calendar, click on whichever date's session you want. You will have the YouTube link there. You just go and watch. You can quickly skim through. You've watched today's session, so today itself we have covered a lot, so you can Just
Due
give
to
through
this,
the.
I could not submit week 6 assignment also. Is it affect on my?
No, you just need to have what 5 or 6 out of 9 or something, right?
I did
Yeah, ma'am,
week
7
5,
assignments.
but I could not submit the week 6 assignment due to my eye allergy, and I'm very upset. My week 6 is very weak.
Yeah, I guess a lot of people who attended all the sessions also complained that week 6 is weak.
Yeah.
Yes. Week
Week
6 was
six
in
is
every
about
sense a
that.
catastrophe, madam. It was a
Then
catastrophe.
from
You just
Sunday,
need to
from
keep doing
Sunday,
again and again. That's it.
from Sunday, I took
What we
all
are doing.
the previous chapters. I previous week first we look after previous week. Then I did week 7. Week 6 I do little questions, but I could not properly. But I did mock 5 and 6, but I got half marks just out of 100.
You should probably go back to week 6 and do, because week 6 actually has the core content. Means you cannot ignore week 6.
Yeah, ma'am. Due to this,
You can watch the live sessions. Everything has been explained in detail. You watch the lectures, watch the live session videos. You should be able to solve. Means you have to keep doing it again and again. I agree that it is heavy, but you have to keep doing it again and again. Then you will get the hang of it.
Okay, ma'am.
Yeah. Okay, we'll pick a norm problem. Ma'am, can you suggest any problem?
I'm not sure about it. Can you do it?
Pick one. Maybe this one. A lot of norms are there. So you have a vector A, B, C. Okay, A1, B1, C1. Which of the following are possible candidates for a norm? So you have square root of A1 squared plus B1 squared plus C1 squared. I'll write it as A1, A2, A3 instead. That will be a better notation. So my A is A1, A2, A3. Question is, can this be norm? For it to be a norm, what are the conditions it should satisfy? Those 4 conditions. 4 or 3. Right? These are the conditions for a function to satisfy so that it will be a norm, right?
Yeah.
Okay. So now, does this satisfy the first condition? Is square root of A1 squared plus A2 squared plus A3 squared greater than or equal to 0? We take the positive square root always.
Should be, because we are having all the square.
Yeah.
It will be always tested.
We take the positive square root of whatever number it is. We take the positive square root, and because the term inside the square root is always greater than or equal to 0, we won't have any negative term inside, right? So this makes sense, and this is going to be greater than or equal to 0. What about this condition? Is this condition satisfied?
Yes.
Again, for the same reason as we discussed earlier, right? Square root of this is 0 means square, this is also 0. And this is 0 means A1, A2, A3 are 0, right? Okay, so the first condition is satisfied. What about this condition? Naturally, no, means because of the triangle inequality that we have for numbers, this condition is naturally satisfied, right?
Ma'am, here then we will take A1, A2, A3, all the 3 values, then less than equal to A mod plus B mod, like that we will say.
A plus B. So you will take A1 plus B1 whole squared plus A2 plus B2 whole square plus A3 plus B3 whole square. This is like the inner product thing that we saw, no? A plus B means the vector A plus B. So A1 plus B1, comma A2 plus B2, comma A3 plus B3.
Okay.
Yeah. So this is always less than or equal to this is nothing but distance from the origin, right? So you can think like that geometrically. Maybe if you try to sit and prove this, it may be difficult, but you can geometrically think of it. You have a point A, you have a point B. What is A plus B? This is A, this is B. What is A plus B?
The third side.
Okay, you complete the parallelogram and then the diagonal is A plus B, right? Yeah, basically the third side. If you have a triangle, then the third side is, okay, fine, let's do that. Whatever is the direction. This is A plus B, right?
This should be A minus B, no? A minus B. Because if you find distance between 2 points, it go like x1 minus x2 whole square plus y1 minus y2 whole square. Should be A minus B.
This is B, this is AB. No, this is the resultant vector, right? A plus B. A minus B will be below. Means we have to take minus B and then do A minus B will be below. This is the resultant vector, the sum. No? Sum of two vectors is. This is the resultant vector, right?
So, ma'am, it is parallelogram.
You can use either the triangle law or the parallelogram law. Anyway, you're going to get the thing.
But, ma'am, in parallelogram, we cannot square, na?
Parallelogram law, A, B, this is A plus B. In parallelogram law, you cannot square. This is P, Q, P plus Q.
Yes.
P and Q going in the same direction. Here, this is.
So, the thing is, we will take, what we will do is, parallelogram law says, you take the parallelogram, you complete the parallelogram. This is A again, this is B again, and then the diagonal is A plus B. Okay, we don't put arrows. So, the same.
So I think, ma'am, you have to draw diagonal. A plus B will be diagonal.
Yeah, this is the diagonal of the parallelogram.
But the diagonal is connecting point A and point B. It should connect origin and that point, na?
Oh, sorry. Yeah. So when we take the triangle law, we will take this triangle, right? This one. Right.
Yes,
this is
now it is clear.
Yeah. So what this says is distance of this point from the origin is always going to be less than or equal to sum of these two distances. The triangle or the parallelogram or whatever. So for this particular function using the triangle law or parallelogram law, you can prove the second condition. What happens to the third condition?
We multiply some scalar too.
What is alpha A? You're going to multiply each component with alpha, right?
Ma'am, here just second condition which you proved okay, it is satisfying. So we will always take like that, or in some cases also we need to prove
No,
that
this particular function, because this is the distance function, this is satisfied, right? Otherwise, it is not always true.
we need to check it like whether it is like we need to evaluate whether it is coming equally or less than like that. Okay.
Yeah. So this is nothing but square root of alpha squared into this. And when alpha square comes out, it will come out as mod alpha, right?
Yes, ma'am.
Positive square. Yeah. So all the conditions are satisfied. So this particular function is a possible candidate for a norm. Means it satisfies all this. So you can use this as norm of this vector. So is it clear how to check the conditions?
Yes, ma'am.
Yes.
Okay. Then A1 minus B1. That is the first component minus second component. A1 minus A2. Will this be a norm? Here are the conditions.
And the first condition will it will not satisfy, no? First condition itself.
That's all, right?
Yeah.
Tell me a vector for which it won't be satisfied.
Ma'am, if we say one condition is not satisfied, so that is
That is sufficient.
Enough, no? Because
Yeah.
for it to be a norm, everything should be satisfied. Even if one is not satisfied, it is not a norm.
here is negative is A2, so just that means it is not a norm.
You just take a number such that take minus 2, comma 1, comma 0. What is the norm of this vector? If this is the definition.
Minus 3.
2, minus 1, minus 3.
Minus 3. That's it, right?
Yes.
So norm of minus 2, 1, 0 is minus 3, which is not greater
Less
than or
than
equal
0.
to 0. Yeah. Otherwise, take this vector. What is the norm of this vector?
Minus
0.
But the vector is not 0, no?
0 cannot be.
So this condition means the second part of the first condition. Norm A equal to 0 if and only if A is equal to 0. That's not satisfied. Then A1 plus B1 plus C1. What about that? A1 plus
The
A2
first
plus
one.
C2. Can you give me a vector?
First term satisfies, so it is no negative term.
No, it could be, ma'am, it could be negative, no? Because.
Take the same vector, no? This one.
Mm-hmm.
What is the norm?
It will be minus 1.
Yeah. Or take 1 comma minus 1 comma 0.
Becomes 0.
The norm
Okay.
is 0.
0.
This is not equal to 0, but the norm is equal to 0, right?
Yes.
This is not. Then max, I'm not going to tell, you're going to tell for this.
Even ma'am, this also does not satisfy.
Which is not satisfied?
This one, because first one itself is greater than 0, it cannot be, because let us say a1 I take -1 and by 0 and -2.
Okay.
Then the highest is -1, or else -3 if I take, then highest will be -1, and that is not greater than 0.
0 is the maximum, no?
Yeah.
Yeah, that way also is fine. 0 is the maximum. Norm is 0, but the vector is not 0. Or you can take a completely. Take -1, -1, -1. Norm is -1. Minimum for the same reason, right?
Yes, ma'am. -1, 0 and 2, or 1 plus 1.
Again, this vector works, right? What about the last one? The first condition satisfied?
Yes, ma'am. Because it will always give positive value, regardless of the negatives.
And equal to 0 if and only if. What about that condition?
Equal 0. And yes. So this will fail then. It could be positive, but it could be 0 also. Then if it is 0 norm, then it will not satisfy then.
No. My question is this condition satisfied? Norm A equal to 0 implies A is equal to 0. Is this satisfied?
Yes, madam.
Yes. Greater than equal to 0 means it is.
So all these are non-negative terms. If the maximum of non-negative terms is 0, then each term has to be 0, right?
Yes.
Yeah, that is satisfied.
Yeah, but ma'am, in the previous example, now which one you took -1? Could you please scroll it up? Yeah, -1, 0, -2, where the highest value was 0, but we did not accept that. But actually, the example, if it is -1, -1, -1, then only this is a clear-cut demarcation that it doesn't satisfy. But if it is 0 also, still we can say it satisfies, right? That here.
No. If it is 0, norm A is equal to 0 if and only if A is equal to 0. Here this vector is not 0, but still its norm is 0. No?
Provided A has to be okay.
Okay, so first condition is satisfied. What about second condition? Norm A plus B is less than or equal to norm A plus norm B. What is norm A plus B?
It will, okay. Ma'am, it will be positive on positive. The values you're asking, ma'am?
Yeah, what is norm A plus B? It is maximum of
A1, A2,
plus B1. Mod A1 plus B1, comma, mod A2 plus B2, comma, mod A3 plus B. So we want to show this is less than or equal to maximum of mod A1, mod A2, mod A3 plus maximum of mod B1, mod B2, mod B3. Again, these are all numbers, so you can see that this actually holds. Using the triangle inequality for numbers, using this, no, you can see that this holds.
Ma'am, then to check to verify this value, so the the value of A1 and B1 we choose, we need to put plug the values and see like how do you
No. This is actually true, no? This is true. So if you plug the values, you won't get. See, if you want to show something is true, you have to prove it. If you want to show something is false, then you can choose numbers. So here it is actually true. You can just observe. It means these are all numbers, no? So this is each term is going to be means this because of the triangle inequality. This actually holds. You can just maybe think about it. It's natural that it cannot exceed this.
Madam,
Yeah.
if this is done, I would like to take you back to inner product again. Sorry.
Yeah. So the third condition is obvious, right? Mod alpha comes out. That thing.
Yes, sir. Yeah.
Yeah. Okay.
Thank you, ma'am.
Yeah. Sure. No problem. Yes, sir. What is the inner product?
Very simple question, madam. It's been bothering me for the past 15 minutes. If I have only one element in basis, let's say 101 is the basis. That means I have the value of x and z as the same, and y is automatically defined as 0.
Yeah.
It cannot be any other value than 0, isn't it?
Yeah, because span of this set is set of all alpha times 101.
Yeah.
That's that alpha is in alpha. So this is nothing but set of all alpha 0 alpha.
Okay. So here I can write it as x0x or z0z.
Yeah. Anything is okay. y0y is also fine.
y0y is also
That's just a notation, right?
Right. Now to this one, if I transform and I add 0, 1, 0.
Okay. So to this set is it?
To this set, I create a affine space. Let's call it whatever that is.
Oh, okay.
Affine space 101 is the element that I'm actually the length that I'm translating it by, and it is alpha. Yeah. Now it is alpha plus 1, comma 0, comma alpha plus 1.
No, this element already belongs to this set, right?
Okay. Sorry. 102, let's say, for that matter. 102. Anything. It's alpha plus 1, comma 0, comma alpha plus 2. Is that as straight as that?
Yeah.
They won't be. That means I am actually on the XZ plane. That's about it. I'm not going out of the plane. If I have to really talk about.
Yeah.
Okay. Thank you. I just needed to get this out. I just want to understand what if I have only one element and in my basis, and if I have this.
Ma'am, you mentioned that the mock for quiz 2 would be this Saturday, Sunday. Those of us taking Python have a programming exam on that weekend. And since we would only have one live session on Friday for week 8, I don't know to what extent we'll be ready, for that, because Saturday, Sunday we would be busy revising for the programming Python exam.
Okay, so you're telling you want the mock to be extended for one more day, is it?
Yeah,
means it will be open even after the.
Or postpone at least by 1 or 2 days so that we are familiar with week 8 also.
Okay.
I mean, otherwise our performance would be below par, and we want to do it in a serious manner.
Week 8 content is very less, most of which I'll be covering on Friday. So.
But it takes some time for us to, absorb it and be comfortable enough
for one more day maybe. Means it will be once the mock is you cannot attempt it live, means that's it, right? It will be like it will still be there on the portal and you'll have the solutions, everything, right?
There's something to be said about doing it within the time frame.
No, it's not a timed mock. It will be open like this weekly mock. No, it will be open for what? Both the days. It's not a timed mock. Means it's not for 1 hour. Are you talking about timed mock or are you just telling?
No, I mean just doing the mock itself would make more sense if we are comfortable with week 8, and we would not have enough time because we would have only one live session, and secondly we would be busy with preparing for the programming exam rather than practicing week 8.
Okay, fine. So what are you suggesting?
Either, like you said, either keep it open for one more day, or maybe postpone it by 1 or 2 days if possible.
Yeah. So we will maybe extend it because not everyone is doing the Python course, right? So maybe we will start on Saturday and keep it for Monday, or maybe I'll ask the team if it's okay keeping it for 4 days or anything.
Thank you, ma'am.
Okay, so shall we close?
Yes, ma'am. Thank you very much, ma'am, for the
Thank you,
session.
ma'am.
Yeah, thank you. Yes, sir.
I'm a little bit struggling in week 7. Up to week 6, I was confident. Week 7, a lot of new document.
Oh, you were confident up to week 6, then this is nothing for you.
Week 7 is a little bit.
Okay, maybe the number of concepts has increased, right?
Maybe after 2 revisions, maybe I'm a bit comfortable.
Yeah, maybe you just, if you're confident with the
week 6, yes,
troubling point should have been linear transformations. If that wasn't troubling, then it's nothing. You should be able to.
Transformations, okay.
Which one?
Linear transformation is okay.
Okay, fine. Yeah, I'll just suggest you.
No, week 9, 10 and all, it will be continuation of week 7 or?
No, sir, no, sir. Week 8 is dependent on inner product, but 9, 10, 11 is completely
new topic.
Multivariable calculus. Yeah.
That will be new topic. Means that and this doesn't have any relation. That's what.
No, week 9, 10, 11 is continuation of the calculus part that you studied in Math 1.
Oh, okay.
Yeah, that's single variable calculus, right? Now you will study multivariable calculus. Yeah.
Oh, okay.
In R2 and R3 and all that, how does calculus work?
Okay. So actually, you mean to say that 7th week means for me 7th week is tough. So if we overcome that, then we can up to week 8 we can manage.
Yeah. It's nothing, sir. You will realize. See, equivalence and similarity. It's just those two concepts, and then what? Dot product. You already know what dot product is. Then you just have to digest inner product and.
Okay. 1 or 2 revisions, yes. Okay.
Yeah.
And any session will be there for mock before means like previously you had, but then you are only mentioning.
No, before quiz we will have. Means
okay, that's
quiz
what.
is a long way away, right?
Yeah.
We are giving the mock well ahead so that you will know where you stand and how you have
correct.
Okay.
Yeah. Thank you.
Okay.
Thank you, ma'am.
Yeah, good night.
Thank you very much,
Good night.
ma'am. Good night.